Continuing on from our last video, we are looking at parametric equations of a line in R2 or 2-space or however you want to call it. And what is a parametric equation? Basically, we're going to write each component, the x and y, of the vector form of the line separately. So remember, vector equation looks like this. So I have my point, my parameter, and my direction vector. Here, we're going to split it up. So let's work through our example. So we're going to split up into x and y as separate parts. And let's take a look. So it's going to look something like this. I'm going to have the x component equals 1 plus t. Where did that come from? Well, I knew that I was starting with an x component of 1. And how many times t? 1 times t. So basically this is 1 plus 1 times t simplifies to 1 plus t. So the operation isn't hard, it's just a matter of knowing what we need to do. And then our y value, y is equal to 5 plus 2t. And we need to clearly state that t is an element of the real. So we know that all values of t are possible. And we also should have had that up here in our vector equation. We also should have indicated that t is an element of the real. We have to properly define something when we talk about it in these circumstances. There's an alternate way of writing it, although we won't use this as much or possibly at all in this class. I can't remember for sure. Our parametric equations, and notice these are equations. This is not an equation. We need an equation for x. We need an equation for y. In R3, we need an equation for z. This can also be written like this. X comma y equals our x component 1 plus t, comma, our y component 5 plus 2t, where t is an element of the real, and so our parameter is showing up in every section for each component for the x, the y, and if necessary, the z component. All right, let's write parametric equations for another line. So we have another line given here. Once again, we should have defined our parameter here, so I'm just going to add this in. S is an element of the real, so there's no restrictions on it. It can have any real value. Let's write our parametric equations. So x is x components, -4 plus 3s, and I'll try to make sure my s's look like s's and not 5s. I'll do my best. And our y is equal to our y component, 2. And how many s's appear here? It's like distributive property. S times -1 is minus s, or 2 plus -1s, or just minus s. Don't forget to indicate and define that s, our parameter, is an element of the real, or if we did the alternate notation, x comma y is equal to -4 plus 3s, comma, 2 minus s, where s is an element of the real. All right, so that's our crash course overview. It's not a terribly complicated concept. We just have to remember to actually do it and understand what the language means when we're asked to find parametric equations for a line. It's basically just, we're taking our vector equation and we're converting it. Let's take a look a little deeper into equations of lines in 2-space in R2 using our new tool, the parametric equation. So the first thing I'm going to do here is look at my question 1, determine if the following points are on the line L. And we have our position, our point vector, -4, 3 plus t, and our direction vector is 3, 2. And we should also, once again, remember to define our parameter as having all real values here. First thing we're going to do is we're going to rewrite our equation as parametric equations. And that's going to be the tool we're going to use to determine if the following points, A and B, lie on this line. And you've done tests like this before, left side, right side check. when dealing with lines in 2 dimensions in grade 10 and 11 and stuff. So this is not a shockingly new concept. We're just using new tools and defining this stuff. So let's write our parametric equations for this line. X is equal to -4 plus 3t. Y is equal to 3 plus 2t, where, once again, indicate clearly that t is an element of the real. And let's test. We'll start with point A. Let's switch our color up here. Point A. So we're testing if -1, 5 lies on line L. If x is equal to -1, so we're taking our x value from here, and we're going to plug it into our equation. So let's take a look at our parametric equation. Instead of x, we're subbing in -1 equals -4 plus 3t. -1 equals -4. I don't need to rewrite it that way. I'll bring the -4 over right away. So -1 plus 4 is 3 equals 3t. T is equal to 1. All right, so we've defined our parameter t in this specific location. So now we can test our y value. Now we can test our y value. So I know the equation for y, the parametric equation is y equals 3 plus 2t. I just defined a value for t that worked for my first component, my x component. So let's see what works. Let's see what we get. 3 plus 2 times 1 is 5. And did we find the value we were looking for? Yes. We saw that when t equals 1, then the x component here is -1, and the y component is 5. So that tells us, therefore, the point -1, 5 lies on our line. I'll just say lies on the line L, just lies on L. Because it satisfied, that value was able to satisfy both of our parametric equations. Now let's try this for B, for the point given in B. So we're going to test if 10, 7 lies on L. So if x is equal to 10, so in order for our x equation, or our first parametric equation, to be true, what value of t are we going to need? So let's find out. So 10 equals -4. And once again, I'm just doing this equation here, but subbing in a value for x in order to find the appropriate value of t that allows this equation to be true. Plus 3t, rearrange and solve. So 14 equals 3t. T equals 14 over 3. Next, now test our y value. So I'm going to plug y into my I'm going to plug this t value into my parametric equation, and this y value needs to equal 7. If it does not equal 7, then this point does not exist on this line. And that's fine. That's why we're testing to find that out. So parametric equation of the line y is equal to 3 plus 2 times our t value of 14 over 3. So that's going to be 3 plus 28 over 3. Let's solve this properly, working with fractions here. So 3 is 9 over 3 plus 28 over 3. It's going to give us 37 over 3. Or if we really wanted, 12 1/3. Now, I don't know about you, but I don't think 12 1/3 is equal to the value of 7 that we were looking for. So this does not equal 7, and therefore the point 10 comma 7 is not on the line L. And in future videos, we'll extend this and apply this to three-dimensional lines as well, so lines in R3, and also check if those points lie. We'll use a very similar test to see if a given point lies on the given line. Once again, sorry about the watermark. If we like this software, I'll buy the complete version and just use it for ongoing videos. But for today, I'm trying it out for the first time, and hopefully it's not covering too much important material as we go. As always, I mean, you can always just pause the moment I scroll out of the way to take a look if you need to, but I'll try to avoid writing under it as much as possible. We're almost done. A couple more things to look at. What else can we do with the parametric equations? How else can we work with lines in 2 space? Question 2a asks us to determine vector and parametric equations for the line containing points e, -1, 5, and f, 6, 11. What are the coordinates of the point where this line crosses the x-axis? So in other words, what is our x-intercept? And can the equation r, -15, 7 plus t, 14/3, 4, where t is an element of the real, also represent the line containing points e and f? Well, let's take a look at this one piece at a time. First of all, I'm going to find the direction vector. So, no, I don't want to graph that properly. We're going to have point E. We're going to have point F. We're going to find the vector that goes from one to the other. That'll be our direction vector. So let's find our direction vector. So part A, I want to find the vector equation of this that describes this line. I know a point. In fact, I know 2 points that lie on this line. Let's find the vector that runs from one to the other, our direction vector. So direction vector M is going to be equal to vector EF. And we can find that quickly. Subtract our x value. 6 minus -1 is 7. And 11 minus 5 is 6. And I'm just not showing my work because we've gone through this enough times now. And I'm going to consider my point E, -1, 5. Let's find a vector equation for this line. So my vector equation R is going to be equal to my point on the line, -1, 5, plus t times my direction vector, 7, 6. And of course, t is my parameter, which I need to define. T is an element of the real. All right, next, let's put this into our parametric equations. So this was our vector equation, a vector equation of this line. Now let's go down to parametric. So x comma y equal to -1 plus 7t. Remember, we're just getting those values from here. Comma, and then the y component, 5 plus 6t. Don't forget to define our parameter. T is an element of the real. So we finished answering A, which said determine vector and parametric equations. So I have my vector and I have my parametric. I'll just highlight them to make them distinct. Let's take a look at what we need to do for B. B says, what are the coordinates of the point where this line crosses the x-axis? So in other words, what is the x-intercept? And as you may recall from previous knowledge, at the x-intercept, we let y equal 0. And basically, honestly, anytime I talk about the x-intercept, and that's something I'm going to find, I just write y equals 0 beside it. Just as a quick reminder, because I mean, conceptually you understand, but sometimes you're busy and you forget, and you're just like, okay, x-intercept, that's when the x is equal to 0, and then you go on to your writing, and then you're like, oh shoot, I found the wrong thing. So I do find it helpful to be explicit and remember and state that y equals 0 basically anytime I talk about the x-intercept. So what? Now that we know that y equals 0, how are we going to use that? Well, we're going to use our parametric equations, similar to the last question. We're going to sub in our value for y into the equation, solve for our parameter t, and then use t to find our x value. So let's go ahead and do that. Y is equal to 5 plus 6t. And I just said that y is equal to 0. So 0 is equal to 5 plus 6t. So -5 equals 6t. So t is -5. over 6. All right, cool. Let's plug that t value into the parametric equation for my x component and find the x value that allows this to be true. So we know our parametric equation from up here, x is -1 plus 7t. We just said that t is -5 over 6, so x is equal to -1 plus 7 times -5 over 6. So x has a value of -1 minus 35 over 6, or x is -6 over 6 minus 35 over 6. So x is going to have a value of -41 over 6. So therefore, the line crosses the x-axis, or we could say the x-intercept of this line is at the point that we just found, -41 over 6, comma, 0. And we're not quite done. We still have to answer C, and C asks us, can the equation r equals -15 comma -7 plus our parameter t and our direction vector 14 over 3 comma 4 also represent the line containing points E and F? How are we going to show that? Well, we can use the tools we already have, and we know that our line is defined based on these 2 points that exist on the line. So we can just go ahead and check and test, do both of those points exist on this line right here? Let's take a look. So I'm going to kind of rewrite the question, and then we'll go ahead and dive in. So can I show that my point E, -1 comma 5, and my point F, 6 comma 11, lie on the line and that's the line that's given here. So r -15 comma -7 plus t 14 over 3 comma 4. Don't forget to define our parameter t as an element of the real. So first thing I'm going to do is convert from my vector form to my parametric form here. So I can rewrite this as x is equal to -15 plus 14 over 3t, and y is equal to -7 plus 4t. Now let's test both of our points. Let's test E and let's test F. I'm running out of room here. Hopefully we can manage to fit this okay. And I don't think this is going to fit, so I'm going to erase the stuff that appears above. I mean, you've already seen it in the video. If you need that information again, just rewind and go back and see what's been erased. As I was saying, now that we have our parametric equation of this line, let's test each of our points. So we're going to test point E, which we recall is at -1 comma 5. All right, just like we just did, if x is equal to -1, let's find the value of t that works there. So we're going to plug that into our x component, our x parametric equation for this line. So instead of x, I'm going to write a -1 equals -15 plus 14 over 3t. Let's solve for t. Rearrange. So we're going to add 15 to each side. We're going to have -14 equals 14 over 3t. In order to get rid of the t, I'm going to multiply at each side of my equation by 3 over 14. Normally I wouldn't show my work, but normally we don't work with fractions quite like this either, so it might be helpful to see that again. So 3 times -14 divided by 14, really our 14s are just going to cancel out, and we're going to be left with a -3. Sorry, this is positive, because when I brought the 15 over, -1 plus 15 is 14. My bad. We fixed it already. We're all good. So 3 is equal to t. All right, cool. So when x is equal to 1, t is equal to 3. Let's plug t into our parametric equation and make sure that our y value is equal to 5. So y is equal to -7 plus 4 times 3, -7 plus 12, or, oops, not negative, +5. Is that the result we were looking for? Yes, I wanted y to equal 5 when x is equal to -1. Confirmed. So, therefore, point E at -1, 5 lies on the line, just like we were hoping for. Now we need to test point F. So same process again, but let's go through it, make sure we have a feel for how to do this. If x is equal to 6, take the x part of our parametric equation, or the x parametric equation for this line. Instead of x, we're going to sub in 6 equals -15 plus 14 over 3 t, and we're solving for t. Add 15 to each side, so 21 equals 14 over 3t. Multiply each side by 3 over 14 times 21 equals t, and we're going to have 62 over 14. And maybe we should put that in a little bit lowest terms. I like to do it just a step at a time. That's how I do it mentally. So, or actually, I think what's the biggest factor that'll go into each? And it occurs to me that that's going to be 7. So if I take a 7 out of both, 62 divided by 7 is 9. Sorry, slight mistake there. Let's take a step back. I'm not going to edit this mistake out. It's easily fixable, and we can see altogether that I made a mistake. When we multiply it across, 3 times 21 is supposed to be 63. That's much better. Over 14 equals t. Divide a 7 out of each. 63 divided by 7 is 9. And 14 divided by 7 is 2. So in lowest terms, t is equal to 9 over 2. Now that we have that value, so let's find our y value. So y is -7 plus 4 times t, and we're testing for when t is equal to 9 over 2. So -7 plus 9 times 4 is 36 over 2, or -7 plus 18, or 11. And what value were we looking for? Hey, we were looking for 11. So we saw that when x is equal to 6, we get a t value of 9 over 2. And when we plug 9 over 2 into our parametric equation, we get our y value back out of 11, which is exactly what we were looking for. So let's just make a little conclusion describing what we just saw here, and then answering the question altogether. So therefore, f 6, 11 lies on the line. And both of these points lie on the line, and both of these points defined our other equations. So this proves that r equals -15, -7 plus t, bracket 14 over 3, 4, where t is an element of the real, does also represent this line, because both of these points are on the line. So therefore, this equation does represent the same line. All right, looking good. We're applying our new skills in new and interesting ways and solving interesting problems together. Finally, we're going to determine if two given lines are parallel, perpendicular, or neither. And let's talk about that for a moment, make sure we're clear on our definitions of those words. Parallel, the lines have the same slope or the same direction vector, and they never intersect. Perpendicular means they meet at one point at 90 degrees. And neither just means I have two lines that are going to meet at some point, but not at 90 degrees. I feel like that looks like too much like 90, but that's just because I'm thinking three-dimensional perspective. So the angle there is not 90 degrees. And we're just going to answer question B as our example here and test this. And how am I going to focus, or how am I going to figure this out? Let's think about what my options are. What are my tools? Well, I know if they're parallel, the direction vectors are going to be the same because they're moving in the same direction every time. If they are perpendicular, then my dot product is going to be 0. So the dot product of my direction vectors will be 0. And if they are neither, then neither of those things are true. If the direction vectors are not the same and the dot product of the direction vectors is not 0, then it's neither. Then they're just two regular old lines that will intersect at some point. Let's read what the note actually says here. Focus on the direction vectors. If their dot product is 0, we know that they are perpendicular. And if one direction vector is a scalar multiple of the other direction vector, so if they're equivalent, they don't need to be identical, but if it's in the same direction, it just has a different magnitude, that's fine. All right, let's actually go through our process here. How do we even find the direction vectors for part B? We're going to answer question B, and we don't have the direction vector form of the equation. We have the parametric equations. That's fine. What we're going to do is go from our parametric form to our vector form. Personally, I find going between parametric and vector pretty easy. I hope you find it to be the same for you as well. Let's take a look. So my line 1 is going to be, we're just going to take our x components here. So we're going to break that up. So 31 and minus 3t. So it's kind of like factoring a little bit here. We're going to have 31. Oops. Yeah, I just said it's easy and then I make a mistake right away. Conceptually, I find it easy. Still make mistakes as we go. Negative 31, comma, our y component, 17. So we have our position, plus t, and our direction vector. We're factoring the t out of these terms here, so minus 3, comma, 1. And I'm just going to erase my marks up here to keep things from getting too cluttered. What is my direction vector here? For line 1, it's going to be negative 3, comma 1. And for line 2, we're going to take our x component, or our initial position components here. So 31, comma, negative 17, plus our parameter. And we're factoring our s out. Sorry, I shouldn't have used t for my parameter. We're going to use s. And let's take a look at those values, and we're going to have s bracket 12, comma, negative 4. So our direction vector for line 2, so m2 vector, is 12, comma, negative 4. All right, this is great. We have our values. Let's take a look if one is a multiple of the other. All right, I was accidentally paused there. I'm not sure how much of the video I was paused for. I'm just going to keep going. And if you missed something significant, you're not sure where it came from, let me know. The last thing I was saying, though, is that we are trying to figure out if our direction vector m1 and our direction vector m2 are some scalar multiple of each other. So can I take this vector, multiply by some value, and get this vector? And in order to do that, I'm going to divide the x components and the y components and see if we get the same value. It's just like when you worked with similar triangles in grade 10 and you had to find the scale factor. Is there some number I multiply the first thing by in order to get the second thing? All right, so let's divide. So I'm going to take the x component from my second vector and divide by the x component from my first vector. So we're kind of doing like m2 over m1 kind of thing here. Is that equal to the y components? Negative 4 over 1. And yeah, it is. Negative 12, or sorry, 12 divided by negative 3 is negative 4. And negative 4 over 1 is negative 4. So, therefore, m1 equals some scalar multiple of m2. Or we can even say it conversely, that m2 is some scalar multiple of m1. It doesn't matter which way we say it, it's the same thing. And we can actually see that the value of the scalar multiple is -4. It's not really too relevant here, but we can say that k is equal to -4. And we can demonstrate that over here. 12 comma -4 is equal to -4 times -3. 1. We're just doing a left side, right side check here, so we shouldn't actually say if it's equals yet, if they are equal yet. This will be the same. There's no operation to perform here. Here we're going to multiply distributive property, 12 and -4. Oh, look, we got the same result. Left side equals right side. Therefore, m2 is equal to 4 times our direction vector m1. Or, if I wanted to write it the other way, m1 is 1/4 m2. We don't need to state it both ways, but we can. Final step is just to state our conclusion. So, therefore, what were we trying to find? We were trying to figure out if these lines are parallel, perpendicular, or neither. We saw that they have the same direction vector, therefore they are parallel. So, therefore, since the direction vectors are scalar multiples of each other, we know the lines are parallel. Or we could abbreviate, or this is the last page. I can't actually scroll up past the watermark, but we'll make do. Or, therefore, since m2 equals -4 m1, so it's just the specific way in which they are scalar multiples, then our line then L1 is parallel to L2. All right, and that is how we can use our parametric equations and our direction vectors to prove if lines are parallel. So parallel have the same direction vector. Perpendicular, the dot product would equal 0, and I'm not going to work through that example, but you can continue on your own and see if maybe in A or C, when you find the dot product of the direction vectors, if it's 0 or neither. So if the dot product is not 0 and the direction vectors are not scalar multiple, so if it was neither, then be the neither situation postulated in the question.